Assalamu alaikum, dear students. We're back with another video lesson. If you remember the previous lesson, we talked about wave interaction. We said normally two objects cannot occupy the same space, but that is not the case for waves. Yeah, two or more waves can occupy or can be present at the same spot or at the same place or the same space, you can say. And of course, that was wave interaction. Of course, we said after that we talked about superposition. We said it is basically the addition or the addition of or the combination or the addition of two waves basically at the same location. And of course, then we had the superposition principle. We said it is basically the algebraic sum of two or more waves. And of course, once they meet at the same, let's say, spot or location or space. And of course, the resultant displacement of the particles would be the combination or the addition of the displacement of the individual waves or particles of the wave, let's say. And then after that, we talked about the constructive and destructive interference. We said constructive is when two waves, for example, are on the same side of the equilibrium, let's say, whether they are both above the equilibrium or below the equilibrium. And of course, once these two waves are meeting, for example, they are traveling, of course, in opposite directions. So once they meet, their displacement would be added in this case. And of course, or you can say the resultant displacement would be the combination of the two. That was constructive interference. And then after that, we talk about destructive interference. We said for destructive interferences, we had two types. We had weakening destructive interference, where the result or the resultant displacement would be smaller than the displacement of the wave with the larger wave, you can say. And of course, in destructive or total destructive interferences, when two waves move in opposite direction, one of them is above the equilibrium and the other one is below the equilibrium. And then of course, once these two meet at a point and they are traveling in opposite direction, the resultant displacement will be zero. That was complete destructive interference. And then after that, we talked about the phase difference. If you do remember the phase difference, basically, if I go short on this, or if I explain this shortly, that would be this. Let's say, for example, we have two waves, as you can see here. Perhaps, or let me explain it here. Perhaps it would be better. Okay, let's say we have two waves. Yeah, if these two waves, let's say this is one of the waves. Okay, and then there is another wave. Let's use a different color for that. Okay, now you can see that these two waves are coinciding, yeah? Or you can say these two waves, of course, they have, you can see that they have the same wavelength, they have almost like the same amplitude as well. We can see that these two waves basically are in phase, we say, or you can say the phase difference between these two waves is zero. So phase difference between, all right, let's make this one proper. The phase difference between these two would be zero. Why? Because you can see here, these two waves are coinciding, or you can say these two waves are starting from the same point, or you can say they have the same what? The same phase difference there. So you can see here, you can combine these two, or take a look. We can also, in terms of phase difference, we can think of this one as well. Let's say this is one complete wave, okay? If you think of a complete wave starting, let's say this is point A and this is point B. This is half a wave, and the other one, of course, would be the other half of a wave. This cycle that you see here is basically, this is what I'm drawing. We have half a cycle. First, let's say one amplitude, two amplitude, and this is three amplitude, and this is the fourth amplitude. We know that four amplitude together would make one complete wavelength. So this is, let's say, one, that is going to be two, three, and four, yeah? So basically, if one of the wave, or if both waves are starting, this wave, or these two waves both basically starting at the same point, so you can say the phase difference between the two is zero. But what if we had a different case? Let's say one of the waves, all right, let's think or consider this scenario as well, where one of the waves, okay, let's say one of the waves is starting at this point here. That is one. The other wave is, let's say, starting at this point here. So what is the phase difference here, let's say? Okay, now you tell me the phase difference here, of course. Now, if we go back to this, all right, or to this one here, okay, one of the waves is starting at this point here, yeah? And then the other wave, you can see, if I like extend this one, of course, you would see that this one here. And then the other wave, as you can see, let's give it a name. Let's call it wave A and wave B here. And wave B would be starting, let's say, so one of the wave would be starting at this point, let's call it wave B, and then the other wave is starting at point A, let's say. So of course the angle or the phase difference between the two is, in this case, is 90 degrees. Okay, now that is another case, and of course we could have another wave starting from this, let's say, we could have another wave starting from this, and then going on from this. If we start from this point, of course, that is basically, or if it starts from this point here, you do know that the phase difference is going to be 270, yeah? Then what about if we have a different case, let's say? Now we have another wave, all right? Take a look. I don't know these wires, okay? Now, so take a look here. One of the waves is starting at this point. The other wave is starting right and opposite to this. Or you could say it would look like something like the image. Let's call this one wave A, and then wave, this is going to be wave B, let's say. Now you can see here when wave A and wave B, or you have two waves that are like this, you can see that it's almost like B is the mirror or the image of, you can say A, or you can say B is mirroring A, yeah? In this case, the phase difference is going to be what? Is going to be 180 degrees. Or, in another way, you can say one of the waves is starting, let's say, from this point, right? Now, that is one of the cases you can say, or you can think or consider this, and then, of course, the other wave would be starting, you can see that? You can start, or starting at the other side, yeah? So, of course, in this case, the phase difference is going to be 180 degrees. And, of course, you can see that on this diagram as well. One of them is above and then the other one is below. Then the phase difference here is going to be 180 degrees. Okay, now we have a question related to this. Question 27 says, using the superposition principle, draw the resultant wave of each of the example below. Now, before we do this one, take a look at what we have here, or take a look at the question. You can see that, you know, like you can see that these two waves, they're crescent trough or coinciding. If that is the case, then of course these two waves are, you can say the phase difference between the two is 0. If the phase difference between the two is 0, then the superposition, or you can say we will always have constructive interference. So the interference is going to be constructive in this case. So if that is one of the cases here, for example, let's say we can redraw this one, or if this is, let's say, 1 unit up and this is 1 unit up, of course the resultant is going to be 2 unit up, all right? For this one, these are both down, so 2 unit down, so you can see here red and blue. The green, of course, would be the resultant of this two. But take a look at part B here. You can see that we have crest, we have trough, yeah? So when we have crest and trough coinciding here, that means the phase difference between the two waves is 180. And remember this, whenever the phase difference between two waves is 180, that means the interference will always be completely destructive here, or completely destructive. So you can see here, this is one of them, right? Let's say this is wave C, of course, and this is wave D. So the combination, or once you add these two together, you'll get a wave that has 0 displacement or no wave at all, because each one of the waves would simply cancel one another out. Okay, now we have another question, of course, as what is the difference between constructive interference and destructive interference? Now, we've learned the difference between the two, but let's go through these real quick one more time. So, of course, in terms of constructive, we do know that or we can say constructive interference is basically the displacement are on the same side of the equilibrium. In order to have constructive interference, the two waves, or you can say the amplitude of the waves, has to be what? Has to be on the same side of the equilibrium. So just like this one, for example, here. Yeah, so this is one, the other one is this is 1 and 2. You can see here the displacement are on the same side of the equilibrium. That is, if we're looking at this part. If you look at the other part here, these two displacement are again on the same side of the equilibrium, but of course this time is below the equilibrium, you can say. So of course we will add them, but once you add them, of course you get a constructive interference. Okay, what about the second point? The resultant displacement is larger than the amplitude of the individual displacement here. That is for constructive. Yeah? What about the destructive interference? In terms of destructive interference, we do know that in order to have destructive interference, the displacement, do they have to be on the same side? Of course not. It has to be on opposite side of the equilibrium. Opposite sides of the equilibrium. So of course the displacement are on opposite sides of the equilibrium. And of course the resultant displacement is smaller than the displacement of the larger wave, okay? Remember this. Sometimes you might say the displacement or the resultant displacement is smaller than the individual wave. That is not necessarily true. Okay, for example, if you have a wave that has let's say 3 units of amplitude, or the amplitude is 3 meters up, yeah, and then the other one is 1 meter below the equilibrium, okay, so 3 minus 1 you get 2, yeah, so 2 of course is, you can say, is bigger than the one that is below here, so not always smaller than the individual waves, yeah, so it has to be smaller than the amplitude or the displacement of the larger wave. Okay, now we have another question here. It says, which of the following waves shown is basically the resultant wave form, okay? So take a look here. Now, this one is very simple to tell, okay? But you need to know, or in order to do this correctly, here's what you're going to need to know, okay? So for example, take a look at those places where all the waves are on the same side, okay? For example, at this point here, you can see that all these waves are on the same side of the equilibrium. Why? Because we want to know, okay, if all these waves are on the same side, we do know that, for example, which one is going to be the resultant or the combination of the other two waves, let's say. Or you can take a look here, yeah? So by looking at this two here, you can easily tell that, for example, now this one is, let's say, one wavelength, this is not wavelength, this is one amplitude, and this is the other amplitude, let's say, and of course, this one here is going to be the resultant of this. For example, if this is 1 and this is 1 again, so 1 and 1, you'll get a combination of, or 2 as a resultant, and this is going to be, or the red one is the biggest here, so of course, it means this red one is the resultant of this two here, right here. Okay, so of course we can say the red one is the resultant, but what is the red one? And of course the red one is Y3. So we can say Y3 is basically the resultant of both, or the combination of Y1 and Y2. All right, moving on to the next question. Right, it says what? Review. Can more than 2 waves interfere in a given medium? The answer to this question, yes. We said for physical matter, for objects, for example, that are around us, this wouldn't be true. For example, if you have one pen, another pen cannot take its place unless if you move this pen, yeah? If you have a chair and a table, you cannot have any other things, yeah? Unless, or you cannot have or put anything else into that, or let's say in the place of that chair and table, unless if you move the chair and table. Okay, but that is not the case for waves, yeah? Because waves can, let's say, interfere, so of course, 2 or more than 2 waves can be at the same place at the same time, yeah? Because waves can interfere. So the answer to this question, yes, multiple waves can interfere in a given medium. Of course, waves are, unlike matter, they can occupy the same space simultaneously or at the same time, allowing their displacement to be algebraically added or combined, or let's say added, of course, or subtracted, yeah? All right, so we have another question, that is question 32, says, what is the resultant displacement at a position where destructive interference is complete? Now that is a very easy one, yeah? Remember, we have 2 waves, okay? What is going to be the resultant of these 2 waves when the, when the destructive interference is a complete destructive? So if you have one wave, let's say one displacement above the amplitude, above the equilibrium, and one is below the equilibrium, so one up, one below, they are moving in different direction, and of course, let's say one is positive, one is negative, so in this case, they will completely cancel one another out. So what is going to be the resultant, or the resultant displacement? Of course, the resultant displacement is going to be 0 because they completely cancel one another. Okay, so the answer is going to be the resultant displacement is 0. What about question 33? It says, when 2 waves interfere, can the resultant wave be larger than either of the individual or the 2 original wave? If so, under what condition? Yes, the answer, or to answer this one, of course, it would be true in case of what? In case of the constructive interference, okay? In constructive interference, we get a wave, all right? Let's use, all right. So in constructive interference, let's say this is one of the waves, okay? And then let's use another wave, okay? So let's say this is 1 unit, okay? Each one of these has, let's say, the amplitude is 1 meter, let's just say, okay? Now, we have blue and black wave here, so the resultant, let's use a different color. So the resultant is going to be 2 units in this case, yeah? 2 units up and 2 units below, of course. And so we can see here the resultant is bigger than the individual waves here, okay? But do we get, will this be true in destructive interference? No, the answer is not. So yes, we will have a wave that its displacement is larger than the displacement of each individual waves you can see here. Okay. Now, we have a new concept which is reflection of waves. Yeah? Do waves reflect? The answer is yes. Okay. Now, if I take you back, let's say to something, let's say grade 11, what happens when you stand in front of a mirror? Let's say, of course, light hits your body, goes to the mirror, then the light will be reflected. You see the reflection, and that is basically how you see the reflection of a wave, let's say, or the result of that is going to be your image. So you see your image, and that happens because of the reflection of light waves here. Now, imagine if we have, let's say, do waves reflect? Obviously, yes. Now we have two different conditions, yeah? One of them, let's say that you have a rope. This rope is, you can see that it is tied to a cord in here, okay? But as you can see here, this end of the rope is free to move, so it can move up and down, yeah? And then, of course, we have another case where the end of the rope is not free to move, okay? So you can see here it's tied, okay? Or you can say at a fixed boundary, the boundary is fixed, so it doesn't move up or down, okay? But this one here, it can move up or down, or you can say the boundary is free, okay? So it is not fixed. So what happens when you send a wave, a pulse, let's say through the rope in here? So as you can see here, once you, for example, let's say move this rope up, let's say just one time, so you're sending a pulse through the wave, yeah? This wave, of course, now it passes or moves through the rope, yeah? Once it reaches this point here, of course, now this rope or this particle on the rope, of course, now it would be moving upward here, yeah? And then after that, these particles, okay. So so you can see here. All right, so this rope would be basically moving upward while it is going downward, you can see here. Now this is where, you know, like the point where the rope is moving upward. You can see that. What happens later on? Later on, of course, this rope is going to move downward because it is a wave, so it's going to, we're about to go downward. So once it is going downward, of course, it causes a wave, sending it back the way or to the place where it started from. So if we start here, we're sending basically a wave here. So now this, because the end is free to move, or the boundary is free, so, and of course we'll get another wave, let's say from the boundary here, and of course this wave, you can see that it is moving in opposite direction, but you can see here the wave is not, the wave is reflected but not inverted. So what would happen if it is inverted? Of course you would see a wave, let's say, that is below this. If this wave, for example, was moving or going to move below the equilibrium, we would have called that one inverted. But in this case, it is not inverted, so we'll go back to this. So we have a wave that is just reflected, remember, okay? So you can see the displacement or the amplitude is still above the equilibrium position. So what do you think will happen when these two waves will meet at the same point here, of course, yeah? So of course we'll get a resultant wave, and of course this resultant will be the combination of these two. These two will be added, we get a resultant or a wave that has both of these two individual displacements, let's say, yes, of course, or if I say the short, the result of this is going to be a constructive interference. Why? Because these two are both above the equilibrium position or on the same side of the rope, okay? Even if they were both at the same side below the equilibrium, we would have an constructive interference as well. But in this case, these are both above the equilibrium, so we get a constructive interference, okay? So what about their amplitude? The amplitude of this, of course, is going to be the combination of these two amplitudes, okay? And so what are the properties of this? Or what happens here, okay? So reflection of a wave at a free boundary, so the pulse is reflected but not inverted because it is not upside down, you can see. Both the incident and the reflected have the same amplitude, and of course the phase difference between the two would be 0, and then of course the resultant displacement would be maximum, and the interference is constructive. We say constructive because these two both would be at the same side or on the same side of the equilibrium. Now, we have almost like very similar case, but this time we have a fixed boundary. A fixed boundary is where the object or this side of the rope, you can see that it is not attached to a ring so that it can move freely up or down. No, it is just fixed, let's say, or tied to the wall here. Okay, so what happens when we send a pulse? When we send a pulse, you can see here, the pulse is going all the way there. Once the pulse is reaching this point, what do you think will happen? Action and reaction. So this rope is basically, you can see, applying a force, you can say, on the wall, yeah? And of course, in return, the wall applies a force back on the rope, yeah? So once this happens, of course, now you can see that the rope is, or the amplitude, or the rope would be basically, or this will give a pulse to the rope, but this time it is downward, you can see here. So this, or because it is downward, we call this one inverted. So you can see here, the pulse is reflected and inverted. Okay, and of course the reflected pulse is inverted. The phase difference is 180 degrees. Okay, so the phase difference between the two is 100 degrees because remember, one of them is upward, the other one is downward. So we see when crest and trough overlap or coincide, of course, the phase difference between the two is going to be 180 degrees. So now these two, of course, they will interfere. Yeah. So what happens, or what will be the resultant of this? Of course, the resultant of this is going to be a complete destructive interference where the displacement will be zero at this point or the point where they meet. Okay, so the reflected, we talked about this, the rope exerts an upward force on the wall in turn exerts a force, let's say, downward on the rope. Okay, and then causes a displacement in the direction opposite to the displacement of the original pulse. The resultant displacement will be zero because of destructive interference, okay, and of course a complete destructive interference. Okay, now we have another concept which is standing waves. Yeah? What is the difference between standing waves and normal waves? One of the things that we have in standing waves is basically standing waves. When waves, for example, move, of course, it has to be in opposite direction, but there is a condition for standing waves. Yeah? Or what do normally standing waves do? They basically store energy. Yeah? That's one of the things that they do, let's say. Okay. Normally, the other types of waves, normally they transfer the energy, but standing waves more likely is storing energy. But so what happens here? Okay, so standing wave, it is a wave pattern that results when two waves, remember, when do we get a standing wave? We get a standing waves when two waves move through or pass through a medium, okay, but these two waves, remember, they have the same frequency, they have the same wavelength, and they have the same amplitude as well. So when these two happen, of course, this two wave, okay, we did say that when two waves pass through a medium, of course, using the law or the principle of superposition, they interfere. Yeah? So at some regions, of course, these two waves would have constructive interference, and some other regions would have destructive interference. As a resultant of all this, we'll get this sort of wave. Yeah, a wave where we have nods and antinods. Nods would be basically the point or the places where the or the resultant of a destructive interference, and of course these are antinods are the resultant of constructive interference. So we get nods and antinods. Yeah, the nods are those locations where the particle movement would be zero, the particle's displacement, or there will be no vibration at these points at all. Okay, and then at antinods would be the point where the particles vibrate with a maximum displacement, you can say. Okay, so this is basically what is called a standing wave. Another reason why we call standing wave, because it looks like that it is stationary. It looks like that it doesn't move at all, yeah? And this is why we call a standing wave. So once again, standing wave, it is a wave pattern that results when two waves of the same frequency, the same wavelength, and the same amplitude are moving past one another in opposite direction at a given medium, you can say. Okay, and then remember, we said what is nod, okay? So nod would be this point here, okay? It is called nod. Remember, if I draw something like this, okay, here's going to be, let's say, the equilibrium position, let's just say, okay? So the nod is going to be a point in the standing wave that maintains, nod, we're talking about nods, okay? So a point in a standing wave that maintains zero displacement. So this is a nod, a point on the wave that maintains that will always have zero displacement, or in another word, there is no vibration for those particles that are the nodes here. Okay, so due to what? Due to a destructive interference. What about antinodes? Yeah, so antinodes are these points, you can say, where you can say a point in a standing wave halfway between two nodes. You can see that if this one node and this is two, halfway in between the two is a point, we can call it antinode. And of course, the displacement is going to be maximum here, and of course, which is basically the largest displacement occur, you can say, yeah? So between two nodes, and the displacement is the largest here. Okay, so now we've learned about nodes, antinodes, okay, and standing wave. Once again, standing wave, it is a wave that results when two waves of the same frequency, wavelength, and amplitude meet, and of course, they have to move in opposite direction, and this is the resultant of that is basically we'll get a standing wave, yeah. And then after that, we've learned about standing wave, yeah. So we say standing wave, of course, or nodes and antinodes. Let's say this point is called antinode, this is called a node, yeah. This point here has zero displacement. This point has maximum displacement here, you can see. And of course, if we consider the amplitude of the two, you can see that the amplitude is going to be twice of the amplitude of or one wave, you can say, or the original wave. Okay, now let's learn a few facts about standing waves, or a few information there. So the standing wave consists of alternating regions of what? Of constructive and destructive interference. So this standing wave that you see, okay, remember those regions that are with antinodes, of course, these regions are the resultant of constructive, or the result of constructive interference. And these points that are called node, these are the result, the effect or the result of a destructive interference. Okay, there is no motion in the string of the nodes here. So we said the displacement is zero, or the vibration, or there is no vibration at all. Okay, now another point is a standing wave can be produced by any wavelength that, of course, allows both ends of the string to be nodes. What do we mean by this? Let's say we want to have a standing wave, yeah? You can have any wavelength to create or to have a standing wave, as long as it allows you, for example, to have the two ends of, let's say, the wave to be nodes. So you can have something like this, that is basically standing wave, yeah? Or you can have something like this, let's say. This is one, and of course, this also is a standing, sorry, not this one, okay? Let me redraw this one here. Let's make this one a little bit nicer so that you know what we're saying here. So this is one, of course, you can see that the end of the two is basically, these 2 points are nodes again, yeah? You can have more than this, yeah? Let's say something like this, let's say. As long as the 2 points are here, or the end 2 points are, as long as these end points are nodes, of course, these can be called, these are actually standing waves. So it doesn't matter what wavelength you're using, what length you're using, as long as the 2 ends are nodes, of course, then we can have a standing wave. Now, minimum number for a node and antinode is basically 2 nodes and 1 antinode. And what do we mean by this? Now, one of the, let's say, like if we have a string here, we can have a standing wave if, let's say, we have something like this. So we said the ends of the string, the ends of the rope, the ends has to be nodes. Yeah. So you can see here, this is one node, N1. You can call it. Let's call this one N1. Okay, and call this one N2. Yeah. So, and of course, here's one antinode. You can say. Yeah. Let's say A. Okay. So here's one of the simplest, you can say, standing wave that you can ever have, yeah? And by the way, here is going to be, you can say the wavelength is going to be the largest here, and how many nodes and antinodes do we have? We have 2 nodes, okay? That is at the end of the strings, yeah, you can say, or you can say at the ends of the string, and of course 1 antinode, okay? So in order to have a standing wave, the minimum nodes and antinodes that you would need to have is 2 nodes and 1 antinode. In standing waves, the amplitude is twice of the amplitude of the individual wave, as you can see here as well. If you have one wave that is this, of course you can say the amplitude is going to be twice, by the way. So if this is the resultant, so one of the waves, let's say it was something Not going to draw the original wave there, of course, but it's going to be, let's say if that is the case, then one of the wave was like this, and then the other wave, let's say, was like this. Then, of course, once you add this to, of course, you get a total, which is going to be this amplitude is twice than, let's say, each of the individual waves. So, or if one of them is, each one of these is 1 unit, of course, the resultant is going to be 2 units, which is 2 units, which is twice the displacement of each of the waves here. Okay, next we have, take a look at this. Only certain frequencies, and therefore you can say wavelength, okay, produce standing waves. What do you mean by this? We said earlier that as long as the two ends of, let's say, the string are knots, of course we can have a standing wave, yeah? So one of the simplest you can say standing wave that you have is, that is the case. Let's say if this is the string of the, or the length of the string that we have, then of course we can say, let me take you to the whiteboard and talk about this in a little bit more detail. So let's say we have a wave like this, yeah? Of course we said if the two ends are, knots, of course we can consider this one to be a standing wave here. Okay, so we have 1 knot, okay? We have 2 knot. Let's call it 1, 2, and there, here's an anti-knot, yeah? Not this one, let's write it here, anti-knot. Anti-knot. Okay, so imagine, or let's assume that the length of the string is just L, okay? So now we do know that, by the way, if we do remember the wavelength, yeah? The wavelength is basically the distance from one point on a wave to the same exact point on the next wave, or the distance between one crest to the next crest, yeah? Or the distance from one trough to the next trough. So if I complete this one, you can see here, this is only half a wave, yeah? If I complete the wave, then the other half, if I draw the other half, then you would see that, for example, this is a complete wavelength, yeah? But that is not the case here, or we don't have this one, let's say. Okay, so we just have this one. So we can say the length of this string equal to, half a wavelength. If you want to know what is the wavelength, of course, you cross multiply, so wavelength equal to 2 times the length, okay? So one wavelength, okay, or the wavelength equal to twice this. So if the length of this string, let's say it is 0.5 meter, then of course the wavelength is going to be 2 times 0.5. That means the wavelength is going to be 1 meter. Okay, now, what if we increase the length, let's say, yeah? Or not increase the length. Let's say we want to increase the, we want to increase the frequency, yeah? If you increase the frequency, of course, the wavelength is going to be shorter, yeah? So here's the case that what we have, yeah? Now here, again, we have another standing wave here, okay? Once again, this is the length, yeah? Now you tell me, what is the wavelength here? You can see that this is, or if we start from this point here, now that is a complete wavelength, correct? So we can say the wavelength equal to the length of the string here. Okay, let's do one more here. What if we increase the frequency furthermore, yeah? Let's say 1, 2, and 3 here. So 1, 2, and 3 here. Okay, once again, the length is still L, okay? And then what is the wavelength here? Now, how to determine this, okay? One way to determine this is basically we know that the distance from this point, let's use a different color, the distance from this point all the way to this, you can say this is one wavelength, yeah? What about this one? This is half a wavelength, yeah? So we can say 1 wavelength and a half. Can we say that? And that is, can we say 3/2 wavelength equal to the length? Can we say this? Well, that is one way. Or, if not, you can just say 1.5 wavelength equal to the length, yeah? So in this case, you cross multiply, and of course, you just cross multiply, you'll find out that the length here, the length or the wavelength, not the length, would equal to what? Would equal to 2/3 of the length here. So in another way, this is 1/3, 1/3. This is 2/3, right? And of course, this is 3/3, yeah? So 2/3 of this equal to 1 wavelength, and of course, this is correct as well. So now, based on this, whether to know if we have, let's say, what frequency or what wavelength creates a standing wave, okay? Let's say we want to know, okay, we want to know what frequency, all right, creates a standing wave, or what wavelength creates a standing wave. Remember this. We said one of the standing wave that we have is this, yeah? So remember this. We have two nodes, okay? And of course one antinode. So based on this we can say, in order to know, as long as the two ends of the string or the two ends of the wave, as long as they are nodes, of course we can call them or make stationary waves. So based on this we can say wavelength equal to what? Wavelength equal to 2 times the length, and of course divided by what? Divided by antinodes, okay? That's one way. Okay, so we have 2 nodes and 1 antinode, yeah? Okay, so based on this we can say 2 times the length divided by the number of antinodes. What do I mean by this? For example, let's say, so we said basically we have a way to determine if the wavelength that we have, whether it's producing a standing wave or not. And remember this, there's a very easy way. If using this equation we can tell, yeah? And of course basically if we have the length and the wavelength, let's say, and then you can easily tell if it is producing a standing wave. Here's what we're going to do. So we're going to find the number of antinodes, yeah? So if we're going to get, so antinode here would equal to 2 times the length divided by what? Divided by the wavelength here. Let me write this to it a little bit nicer. So once again, 2 times the length divided by the wavelength. If you're going to, the answer of this or the resultant of this, the result of this, if you're going to get a complete number of antinode, that means that wave, of course, would produce a standing wave, okay? So if the result is going to be whole, all right, that means, of course, there is a standing wave. All right? But then if the resultant is not a whole number, then of course there will be no standing wave produced. Okay, so of course we have questions. You will see more about what we're going to do. But okay, so to find the wavelength, if the length and the number of antinode were given, by the way, if the length and the number of antinode were given, you can easily tell. We can find the wavelength, let's say in that case, of that standing wave. Let's say if not, if we have the wavelength and the length, we can see if that wavelength and length are going to create a standing wave, just like we said. If the number of amplitude is going to be a whole number, then of course we can, that means there is a standing wave produced, okay? Now, sometimes maybe the number of nodes and antinodes are not given, so how can you tell? Remember this, or all the waves that we had previously. Let's say one of the simplest wave that we have, we said we have this, yeah? So as you can see here, this is 1 node and this is 1 node, so 2 nodes and 1 antinode. So if you want to, for example, find the number, or let's say find the number of nodes and antinodes, if the number of antinodes is given and you are asked to find the number of antinodes, in this case we'll say nodes minus 1. So we have 2 nodes, yeah? 2 nodes. If we want to find the number of antinodes, so we'll just say 2 minus 1, because here's the equation, yeah? We have 2, yeah? 2 minus 1 will get 1 antinode, and that would be correct, yeah? Let's say we want to find the number of nodes, you're given the antinode. So we have, let's say, 1 antinode, or a wave that has 1 antinode. So if you want to find the total number of nodes in this case, we'll just say the number of antinode plus 1, yeah? So of course we get a total of 2, and which is very similar to this one here. Or take a look at this one. How many nodes and antinodes do we have? 1 node, 2, 3, and 4, yeah? If I want to find the number of antinode, I'll just say 4 minus 1. So I must have 3 antinodes. So let's count. 1, 2, 3, yeah? That is one way, yeah? Now there is another way. Let's clean this. There is another way, for example, if I start with the antinode this time, how many antinodes do I have? 1, 2, 3, yeah? So 3 antinodes. If I want to find nodes, we said to find number of nodes, antinode plus 1, yeah? So 3 plus 1 will get a total of 4 antinodes. So count with me if it is correct. 1, 2, 3, and 4, and this is correct. So using this equation, we can find the number of nodes and antinodes always. Okay, now, few information about this, yeah? About nodes and antinodes. Now, remember this. Once again, let's draw standing wave here. Okay, Now these, of course, the amplitude and wavelength, all these has to be the same. Here you can see that it's not precisely the same, but you know what it is. So the separation of adjacent knot is half a wavelength. So this is the separation between adjacent knots. So let's say this is, I think I'll have to make this one a little bit better to see this more clearly. So you can see here the separation between two knots, yeah? So this is one knot and this is another knot, yeah? So this separation between the two is half a wavelength. Why half a wavelength? You can see that if you consider this is only half a wavelength, yeah? If we're going to complete this one here, then of course we'll get one complete wavelength, yeah? This is one wavelength. So, but if we consider this two here, of course this is only half a wavelength here. So this two here, let's use a different color just in case. So this point and this of course is half a wavelength. What about if it is the separation between two adjacent antinodes, yeah? And of course that is the same, it's going to be half a wavelength, yeah? But what if we have something like this? Let's say we have this standing wave, of course. The distance between, let's say, one antinode and it is adjacent, and let's say antinode and it is adjacent knot, let's say, or two, one knot and one antinode like consecutively, one after another. So you can see that this is only half. Is it half or a quarter? That is going to be only a quarter of a wave. If not, you can go by the number of amplitudes, yeah? So this is one amplitude, you can say, yeah? And of course, this is another amplitude here. So this distance, or the distance between this all the way to the other end, is going to be half a wavelength, yeah? So the distance between one antinode, okay, and a knot is going to be half of, you can say, or quarter in this case, yeah? They cannot say half a wavelength, yeah? So, or you can see this is half a wavelength, we're taking half, so it's going to be 1/4. So the distance between one antinode and a knot, of course, is going to be 1/4, 1/4 of a wavelength. But what if the distance was, for example, the distance between one knot, I think I misexplained the other one, but still, the distance between, let's say, two consecutive, knots. So one knot and one knot is going to be half a wave, antinode and antinode half a wavelength. If I start from this point to the other point, that is also half a wavelength, yeah? Starting from one knot to another knot, that is half a wavelength. So remember all this, yeah? Okay, so separation of two adjacent knots is half a wavelength. Separation of adjacent antinode, half a wavelength. The separation between two antinode, where the phase difference is 180, that is one wavelength. That is a different one, yeah? So I want you to take a look at this one here. We're talking about the distance between, or the separation between two antinodes with a phase difference of 0, okay? So let's say we have this. So there is a standing wave, yeah? So we have two antinodes, yeah? So let's say this is one antinode, okay? And then of course, with another knot, let's say two antinodes of a phase difference of 0. So can I say, I should have drawn a different color so you could see the difference between the two. If this is one, this is the other one, okay? So we have, let's say two, one of is blue and the other one is red. So take a look here. Can I consider, you can see that it says the distance between two antinodes. So is this antinode, because this is one and this is another antinode, but is this antinode is in phase with this one here? You can see that this one is going to be you can say that the antinode of the other wave, you can say, yeah? So of course the phase difference of this, you can say, would be different from the other one. So in another way, the phase difference between this and this one, of course, it is going to be 0 here. Then of course we can say the distance between this to the other one, then this is one wavelength. So you can consider or count the number of amplitudes. We said 4 amplitudes make one complete wavelength, yeah? So one amplitude, you can say 2, and this is 3, and of course this is 4. So 4 amplitudes together would make one wavelength. Okay. Now moving on. All right, now section review, yes? It says a wave of amplitude 0.3 meter interfere with a second wave of amplitude 0.2 meter. What is the largest resultant displacement that may occur. Yeah? Remember, we want the largest resulting amplitude. So if we want the largest, then of course we'll have to use constructive interference. And in constructive interference, of course, we're going to combine their displacements, correct? Yes, well done, very good. So using this too, one of the wave, let's say, so here's one of the waves. Okay, let's draw the other wave using different color. And one of them is 0.3, the other one is 0.2. So let's make this one a little bit bigger than the other one, okay? So once you add these two together, of course, we get a resultant. And this resultant, of course, is going to be what? It's going to be, you're going to add this one, 0.2. You're going to add 0.3 together. So, of course, you get a wave that is 0.5, let's say, of amplitude. Yeah? If it is meters, of course, it's going to be 0.5 meter here. Let's use a different one. Okay, so this one, or the resultant of this one is going to be 0.5 meter. Okay, so add their amplitudes together. Okay, so amplitude 1 and 2 together, 0.3 and 0.4, 2, you get 0.5. Second one here says, a string is rigidly attached to a post at one end. When it says rigidly attached to, that means the end is not free to move, okay? It is bounded, yeah? So if that is the case, remember, several pulses of amplitude 0.15 sent down, 0.15 meter, sent down the string are reflected at the post and travel back down the string without loss of amplitude. So we said, let's continue with this, okay? So what is the amplitude at a point on the string where the maximum displacement of the two pulses cross, okay? So we said for a pole, if we're sending the end is tight, all right, it is fixed, it doesn't move up and down. So if you send a pulse up, for example, and of course the pulse that is reflected would be inverted, yeah? So once these two meet at a point, of course, then the resultant is going to be 0 here because one of them is positive, the other one is negative with the same amplitude, no loss in amplitude. So of course, we'll get 0 as a result of the displacement. Question 3 says, what would be the amplitude of a pulse of item 2 if the same pulse were sent down a string whose end is free? If it is end is free, we said it's not going to be inverted, yeah? They will be both on the same side of the equilibrium. We will add them together. So 0.15 plus 0.15, you'll get 0.30 as a total or as a result. And of course, it's going to be constructive interference. As for question 4 says, a stretch string fixed at both ends of a 2 meter long string, basically, okay? 2 meter long. What are 3 wavelengths that would produce a standing wave on the string? Name at least one wavelength that would not produce a standing wave pattern and explain your answer. We can say, we can try different numbers, of course, with this, yeah? It says, what are 3 wavelengths? Remember this. So we have a string that is 2 meter long, all right? 2 meter long. So if we want to know what wavelength, we have the equation. So wavelength equal to 2 times the length divided by the number of antinodes, yeah? Okay, so let's say what wavelength, yes? Of course we can, let's say, we can have different number. If we have 1 antinode, what would be the wavelength in this case? So let's say 2 times the length is 2 divided by 1, so of course 4 meter, yeah? So of course a wavelength that is 4 meter would produce a standing wave. What if we have 2 antinodes, yeah? 2 times 2, then divide by 2, then of course we get what? We get 2 meters. So now another wavelength, a 2 meter wavelength would also produce a standing wave. Another one here, let's say if we have, let's say 3 antinodes, yeah? Well, we can have 4 antinodes, you can say, in order for easy calculations, yeah? So 2 times, let's say, 3 antinodes, yeah? So let me do this one. Let's move this one a little bit, okay? So 3, yeah? 3 antinodes. So 2 times 2 divided by 3, that is basically 4 divided by 3, yeah? 4 divided by 3, that is equal to 1 point something, yeah? If I'm not mistaken, is it 1.3 or something? That is basically meter. So 1 point something meter wavelength would also produce a standing wave. What wavelength will not produce a standing wave? Of course, you can say any wavelength that does not produce a whole number of let's say, antinode, then it will not produce a standing wave. Let's say we have, let's say, what wavelength would produce, let's say, 2 times the length is 2. Remember, in order to not to have a standing wave, we should not have a whole number of antinodes. So let's say, I don't know, let's say 3.5. So in this case, 4 divided by 3.5, you get a number, yes, in meters. So this wavelength here will not produce a standing wave. Okay. Question 30 is easy as well. Question 34, I believe we're going to do this one, which is basically the same thing here. Remember this, it says we have a string that is basically 3.5 meter long, okay? It says which of the following wavelength will produce a standing wave on the string. How do we know like which one of these wavelengths will produce a standing wave? Of course, we're going to use this equation, but this time we're going to find the number of, not this one. We're going to find the number of what? We're going to find the number of amplitudes here. So we'll say amplitude 2 times the length divided by the wavelength here. So we're going to try these wavelengths out. If we get a whole number of antinode, that means these wavelengths will produce a standing wave. And if we get a fraction here, not a whole number of antinode, then of course this wavelength will not produce a standing wave. And I'm afraid that is the end for our session for now. Okay, stay tuned for more sessions. We'll continue with you. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum.